So we'll just draw one of them there now. Tangent question mark. So a very simple equation. X squared plus y squared equal to 1. We have shown that this is the same as saying that the distance from, say, a point xy to 0, 0 is equal to 1. I won't explain that. But what is this curve? I won't explain this bit. But what is this curve? Okay, I'm going to start drawing some of these points. So here's one. Oh, a bit extreme. Here's one. 1, 0. Here's one. Minus 1, 0. Here's 1, 0, minus 1. Here's 1, 0, 1. These are all points whose distance from 0, 0 is 1. How can I get more?
You can do a circle around
Just a circle. Should be a circle anyway. So this is what you call the equation of the unit circle, and the idea is that solutions of the equation, if plotted, are on the circle. It's not a function because, for example, at x equals 0, there's two outputs. Now, as it happens, it's two functions glued together. What you have is the top, f1, is plus the square root of 1 minus x squared. And the bottom, let's call it f2, is minus the square root of 1 minus x squared. You find that by solving the x squared plus y squared equal to 1, solve that equal for y. You get y in terms of x. And you get it's two things what's called glued together. In theory, you could find slopes of tangents like that. Take the equation, solve it for y, get the function, and then differentiate it. But the problem is as soon as the curve is any bit more complicated than a circle, you can't find all the branches. So like if you just kind of draw kind of a really squiggly thing, or it's not even that it has to be a squiggly thing, just something that you can't really solve the equation. So for example, x squared y squared plus y cubed minus, let's make it really horrible, e to the y equals 0. You cannot solve that for y. It still gives you a curve, but you can't solve it for y. So we're in a bit of bother. Okay. But basically, and there's not a very good picture here. If we just look at the picture on page 120 for a moment. What that shape remind you of anything, by the way? Pardon? Airplane window, yeah, something like this. Okay. Now it's a bit out of scale, but that doesn't matter. So the way we do it is, like we did at the same theorem that says you can do the parametric differentiation. Says if you have one of these curves and it's nice, and as long as you stay away from the bad bits. Bad. Why is that bit bad?
Straight.
Not 0, but it goes straight up. because that's not a slope, it's not a slope. So that and other where it crosses, where it jumps. Obviously points here that aren't on the curve you can't do either. So what the theorem says is that if you're near a particular point, say near the point 1, 2, that while you might be able to actually find y as a function of x, that theoretically there is a region of the curve that is the part of the graph of a function. So between, say, these 2 points, and I could go as extreme up to the zeros, but I just have to go locally. Locally just meaning near the point. As long as I'm close enough, a part of the curve is the graph of a function. So if I just forget about everything else apart from that bit, that is the graph of a part of the graph of a function. Each x value only has one y value. Say for example x equal to a half, there is only one y value above it. And what that allows you to do is say there is a function, and bizarrely you can differentiate it even though you don't know what it is and you can't find it. It's a bit weird, but it works. So let's see how it works. Back to the previous page. So for example, if you see y squared somewhere, now this is the bit where I have explained it. It's difficult, I'm not going to lie, and a lot of people, most, sometimes all, will not kind of think of this so much, the theory, and do just kind of do the problems. But I think you're better off trying to, or at least see it once anyway. So if the question is, so what eventually we're going to be doing is we're going to be differentiating both sides of the equation. And the issue is that if you see y squared, really we're talking about near a particular point, and near a particular point it is the graph of function. So it's not just an independent y, you think of it as y as a function of x. And then we want to differentiate y as a function of x squared, for example. Say we want to differentiate this, say we want to differentiate this y squared. You have to understand it's a function of x. We don't know what it is. What will I need to differentiate this? Chain rule. Outside, inside. Outside is x squared. What is the derivative of x squared? 2x. Evaluated at the inside, which is, what's the inside? Y of x. Now what we're going to do is we're going to get in this habit of, we're going to write the y as y of x once. And it does a few things. It shows us that theoretically we could know the theory, but it's also going to help us see the chain rule. Because if I just ask you to differentiate y squared, especially after the section after this, there's going to be a temptation to say what? Derivative of y squared?
2y.
2y, and that would be wrong. It's more complicated than that. This is wrong. So we're going to write this y as y of x. It'll help us see chain rules. Then we're going to differentiate things with this like the chain rule. And the end of the chain rule is you must multiply by the derivative of what's inside. The problem is, I don't know what the inside is. I need to multiply by the derivative of what's inside. Any idea what I'm going to write? Some said here. No? So if I don't know what y of x is, I don't know what y is, what am I going to write down as its derivative? I can pretty much, I just have to write down the derivative of y with respect to x.
That's dy over dx?
dy dx, yeah. Now this written here, this seems like complete nonsense. This is going nowhere. But what happens is the following. We start with an equation in x and y, This is what's called, so we're going to be thinking about a specific point. So in theory, you could solve for the y. So this is what's called a functional equation. So the y, theoretically you could solve for it, you can't do it, but theoretically you could. And so what you can do is essentially you've got two things that are equal. So an example of something like this, by the way, would be, say, sine squared of x plus cos squared of x equal to 1. This could be maybe y squared. And maybe the solution of this is actually cos of x, as it is. And what you can do is you can differentiate both sides with respect to x. Okay, you'll see it in practice, presumably after the break. If you differentiate things with x's, what do you get?
Can you write that? Sorry, can you write that d over dx as square bracket y, then sine x in the smaller bracket, the way you've written it up there? So you just take
okay, so actually what would happen here, in other words, yeah. So what would happen here is we'd have to differentiate sine squared, which is it's sine x all squared. Squared outside, the outside function is squared. What's the derivative of x squared? 2x. Evaluate at the inside. What's the inside of this? No, what is the inside of it? No, sine x. Yeah. Times the derivative of what's inside. What's the derivative of what's inside of this?
Cos x.
Cos x. Okay. Plus. Now I will be, when we do the examples, I will be writing y of x. Oh, I definitely don't have space here. So the outside function here is x squared. What's the derivative of x squared?
2x.
2x. Evaluate the inside. What's the inside of this?
d1.
No, what is the inside of this?
X. Y, sorry.
Y. Times the derivative of what's inside?
dy dx.
dy dx. And then you're going to differentiate both sides. What's the derivative of 1?
0.
0. So what's going to happen? And what you have now, if you differentiate one of these things, like this one theoretically you can solve y as cos x. But you won't be, well, that one you can do it. These you can't. So if I differentiate one of those equations, so there's one, sine squared x plus y squared equals 1. I differentiated it. So if I differentiated the stuff roughly with x, what do I end up with? Stuff with x differentiated give me stuff with x. Yeah? So sine squared x gave me stuff with x. And what did the stuff with y give me when I differentiated it?
dy dx.
It gave me stuff with dy dx and stuff with y. So you end up with an equation in x, y, and dy dx. Can you solve that for something? Well, you can solve it for dy dx. And so you can end up with, without ever knowing what y is, you can have dy dx in terms of x and y. It has to be in terms of x and y because it's not a function, it matters. Say you take x equal to 0, that's not enough. Are you talking about that one or that one? You need x and y. So you need 1 and 2 because if it was 1 and minus, if you just said x equal to 1, it'd be which one? Which one? Okay, we might do, how we do for time?
3 minutes.
Okay. Yeah, when we'll come back around 23 past or so, and we'll do an example just to see how they actually go.